Hello. Now we want to talk about stability of ships. What we directly mean is so-called core stability, but more precise, it's yaw stability. And I will tell you a little bit about stability, but first, as an introduction, I'd like to show you a very simple example of stability. So, for instance, this brush, if I try to balance this brush upright, so I need to find the equilibrium, because stability is always addressed to the equilibrium condition. And if I get it go, it falls down. So it's highly unstable. And it falls until it's in this position. Is that a stable position? Yeah, it is. Because if I change it a little bit, it always goes back into stability. It's like my father on the sofa. When my mother tried to get him out of a stable condition, he was very stable and remains there. So we talk about stability. It's a property or characteristic of the steady state equilibrium condition, and there are conditions which are stable or which are not stable. And we are talking about the course, or better, yaw stability. This means we have the ship here, it is a tanker. And I push the tanker now to, let's say, full ahead. It's a speed of about 15.8 knots. And you see the tanker is not really going straight because it's a single screw vessel. And due to the propeller effect, you need a certain rudder angle to stabilize this rudder. So it goes a little bit to port side, so we need a rudder angle to starboard. This is about ½ degree, so now it's, 0.8. So it's nearly 1 degree. It's, only to keep her on a straight track. This has nothing to do with stability. It's the propeller, it's the effect of the propeller revolution and its direction. So how can we, check whether this is a stable situation or not? On one hand, we could generate a small heading deviation, like this here. So we go to 2 degrees or whatsoever. So if we change it a little bit, it remains straight, but it deviates a little bit from the course. So this is not, so this obviously is a stable condition. So now it's back to 0. So what others could we do? And there's a specific maneuver which is called pull-out maneuver, and I will perform this for you. Pull-out means we use the rudder to about, 20 degrees will be enough. 20 degrees, maybe 35 degrees, then we can. So this is 30 degrees now. And the pull-out maneuver means you go into the turning circle, and after a certain heading deviation, we don't need to go for a full turning circle, but I will do it here only because we don't have to spend time for it. So here I add a maneuvering point, and now I change the rudder back to the initial part. So what we see is this ship goes very fast on a straight track, and it's not turning anymore. So if we do that here, for instance, so the rate of turn is nearly nothing. And if we would do the same thing to the other direction, so we go back to the initial position now, and now we choose the rudder to minus to the other side. So this is 30 degrees now. And if we release the rudder at this position, then you immediately see, okay, the ship is going back to the straight stable equilibrium condition. So you might ask, what is, how to say, supporting stability, or what is counteracting stability? One major driving factor is the trim of the vessel. This is a tanker in ballast condition, so like this. And if you would use the same ship but trim to the bow, then you have a total different situation. And I will go back to this situation, and I change now the ship. I have to reset the ship here. And now we are looking for another ship, and we will use the same tanker but in laden conditions. So we would go now with full ahead, 15.3 knots. But you see already the difference here. Oh, sorry. Now I will make it a little bit smaller. The difference is the ship immediately goes, it's not going straight, it's going into a turning circle. I change the scale a little bit, and you see it in more detail. So this is what happens here. And so the first idea is, there might be a propeller effect, a paddling wheel effect, so to say. We apply the same rudder angle we had before, 0.9. It's not enough here, but if I increase it, 1.2, so it's now 1.4 degree rudder angle, 1.5, 1.6, 7, 1.8, and then you see what happens now. A change from 1.7 to 1.8 degree of rudder creates or changes from port turning now to starboard turning. So this indicates already a very high instability, and this ship starts turning from its own will, so to say. So how would look the pull-out maneuver then? I go into the other scale, and so we have the pull-out maneuver with full rudder, 35 degrees. What you see here is the turning circle is smaller than the turning circle with the ballast version of the same vessel. The turning circle, specifically the steady state diameter, is smaller. And if you do the pull-out maneuver, same as we had before, so here, what you also see is the drift angle is much more bigger. Sorry. So now I say add a maneuvering point, and then we switch to, it should be the same as we had before. We need to adjust the rudder to 1.8 because that's the equilibrium condition. And then we show the result. So the ship is going into a turning circle. 1.8 was the neutral, the rudder angle of neutral effect. And you see, it doesn't help. The ship continues to turn. You would even see the full picture here. So this is the turning circle. Here we put the rudder amidship, and not amidship to the neutral effect degree, but still the ship is continuing to turning and goes into the turning circle. So if I repeat now the maneuver to the port side, I go back to the initial position, to 0, and now I put the rudder not to starboard, but full to port. So this would be the turning circle to the port side. By the way, specifically for these unstable vessels, the turning circle might be going a little smaller. And then we go to the next position where we put the rudder amidship, here. And you see the result. The ship continues turning to the same direction as it has before. So if we have a starboard turning circle as we had before, it continues turning to starboard. And if you start turning to port, then it continues turning to port side. So this is the typical effect for the unstable vessels. So if the ship is trimmed to the bow, then the turning circle is smaller. You can imagine why, because the drift forces, they are really attacking the ship on the bow, and so it's nicely turning, and the damping forces at the stern, because the stern is going out of the water, they are reduced. So the unstable moment wins, and the ship turning circle is much more smaller. There are other maneuvers which we could do, the so-called spiral test. This is investigating the ship characteristic with several rudder angles and then looking for the rate of turn. And the other maneuver is the zigzag test. And for the spiral test, you get the result that in the range of about, how to say, for this ship, 10 degrees port to starboard, there could be a turning to port or starboard, so it's not decided. And for the zigzag test, you get very high overswing angles up to 30, 40 degrees for the unstable vessels, whereas for the stable vessel in ballast condition, it's only 10 degrees. Okay, this shows the effect of stability, yaw stability.